Hello, my name is Erwin Lubbers and I'm the lead AI engineer of GILO Technologies. I'm also the CFO of GILO, and besides that, I'm a lecturer at the University of Applied Sciences in Rotterdam, where I teach subjects like finance in IT and data science. Today in this presentation, I like to talk about AI and how GILO uses AI classification to classify documents and sentences. And why do we want to do this? It's to know what the user is writing about, so they can actually get the right advice and guidance. Okay. So it's basically natural language processing, as in how to make a computer better understand language, which is quite challenging, as you will soon find out. So first of all, why do we need to categorize text? Well, certain words, certain keywords can have a different meaning in a different field. Here you see an example for stock. In finance, stock is an ownership of something, a share or equity, as in I bought hundreds of shares of stock of Apple on the New York Stock Exchange. Well, if you think about business administration or accounting, stock can mean an inventory, like Apple has 1 million iPhones on stock. So by knowing the field, what the user is writing, we can actually give him advice on what the word means. A second thing is citation advisor. We have a number of citations in all kinds of fields. They're ranked on what words, what keywords are used in them, also like how many citations they have or how recent the article is. And another factor is the field. If the field is the same as what the user is writing about, the citation is bumped up in the list. Finally, I like to talk about acronyms. We can convert an acronym to what it actually means. For example, we all know IP as what is your IP address? That's Internet Protocol. But however, if you talk about business administration, IP actually means intellectual property. There are several other terms that link the same acronym as a different meaning in a different field. Now, if you don't know the field, you suggest the wrong term for an acronym and you get odd sentences, and you might figure this out pretty quickly, but think about a student that's not used to writing or terms that well. He can just be fooled by the wrong acronym. So, for example, Internet Protocol can be registered in any one of the following three methods: copyright, trademark, or patent. Well, first glance, it sounds okay, the sentences, but it's clearly Internet Protocol, intellectual property, not Internet Protocol. Okay, so my first attempt to classify is simply by counting keywords. At GILO Technology, we have a really thorough taxonomy of business terms. We have almost 20,000 of them by now, and they are all labeled in field, subfield, and subject. So the thing is simply take the user's document, tokenize the text, and compare it to the taxonomy, and out comes a long list of keywords. And we simply count the field where that keyword is in, and the field that has the highest number should win. Pretty easy. This is my own thesis I wrote for Masters in Financial Management at Erasmus. And as you can see, finance has the most keywords, and that is actually correct. Second is business administration. I see some real estate, some accounting, some statistics. Well, that all seems fine. However, it's not always this clear cut. And my thesis was, well, edited a lot. And some of the work of the students is different, so to say, and it can be much more, well, less accurate. So by testing it, I only got about 2/3 right, an accuracy of 65%, which is, well, we can improve on that. How are we going to improve on that? With AI, an AI document classifier, which is a pretty, well, established thing in classification world. With documents, you have a lot of text to work with. There are a lot of terms in there. So an AI should find patterns in the words and be able to classify it. So the first step is we create a structured data set. We did so by taking about 1,200 research articles We labeled them in our 18 different fields like finance, economics, marketing, etc. At the end, we put them all in one data set, but we split it in a training set, which is meant to train the AI. We'll later get in that thing. And there's a test or validation set, which used to, after the AI is trained, to check if it's properly trained by exposing it to new material. As in, has the AI learned only how to identify the material that it's trained on, or can it actually make general predictions? Now, the first thing we have to think about is a computer does not speak English. A computer does not speak Dutch or Mandarin. It only knows about bits and bytes. So we need to get our text and convert it in a format that AI can understand. We do so by creating a vocabulary. It's basically a script scans through all the 1200 documents. It identifies all the words. It creates a vocabulary where the most used word is simply labeled 1 and the least words, well, just name any number, in this case 25,000. So here in this example, we can see the word de is the most used, of is second, and is third. Well, that's a bit unsurprisingly. Also very generic. I don't think the AI will, well, find useful patterns with the word de in it. Halfway the vocabulary, we find the more interesting things. For example, model is 31, market is 32. It's business-wise still a bit generic, but at least they're business terms. Now, if we go all the way to the end, the least used words in our 1200 documents contain things as non-stochastically. I know stochastics, but non-stochastically, I doubt that's a real word. Alice Patrick, well, that sounds like a name, not a real word too. And international, I guess the in fell out of international. Computers, well, they don't know what's a real word and what is not, so they just pick any tokenized, well, set of characters and assume it's a word. So the very most used word and the very least words are not that useful in the AI to recognize patterns, but it's the part in the middle we like most. Be it as it may, in the next step, we take one document at a time, we run it to the vocabulary, and we simply count the words. And we put that in a row of the matrix you see kind of at the bottom left. For example, the first row where 492 is highlighted contains the word de 492 times, of 304, etc. International is not found in any document there, I see. We do the same for every document until it creates a matrix. This matrix is 1200 rows deep, as in 1200 documents, and it has 25,000 columns representing the word count for the 25,000 words in our vocabulary. Now, this matrix, really, this is the ideal input for an AI. I believe, well, about anything I imagine is put in a matrix format before it's put into an AI, and it's the main part of the data pipeline, and well, that's usually more work than the AI itself. Why this matrix? It's because of linear math or matrix multiplication. It's a very efficient way of computers to calculate stuff. Normally, you would go through all the numbers in an array, in a row, or whatever your calculations are about, and you would like multiply that number, then the next, multiply that. It's got to iterate through everything. That takes a long time. With linear math, you just take the whole matrix, do a dot product of it, and end up with a new matrix that's multiplied by 2 or whatever your thing was. And now this is really used a lot in AI deep learning. It's also the basis of, for example, video games with 3D ray tracing, and it probably comes in other things like cryptocurrency. So I'm not an expert there, so don't pin me down on that one. Okay, I guess we're ready for the deep learning model itself now. In the middle, you see a representation of a simple deep learning model. You got the little circles, they're the neurons, and they're a bit like the neurons in your brain, as in they have functions in them that can send a signal. All the black lines, there are the connections between the neurons. For example, the input layer, every single neuron has connections to every single neuron in the first hidden layer. And the hidden layer is connected to the output layer. Usually there are multiple hidden layers. On all these connections, you have weights. And these weights are what that are used in the deep learning training. Now, to give an example, we have the first row of our matrix, which is the first document of our data set. We take the vectorized version, it goes in the input. Then the weights, they multiply the data with certain weights till eventually it arrives at some outputs. Let's say, for example, it predicts economics. Now it looks at the real label, which was finance. So it said, that is not right. On a second attempt, it does it again from the inputs, but it changes the weight slightly. By changing the weights, the activation functions in the neurons may trigger differently or may not trigger at all or trigger when they didn't used to. That will result in a different output. For example, many tries later, it finds, oh, there it is. It's in finance now. That is correct. I did it well. It does a similar thing for all the documents. The weights are constantly changed, and in epochs, it's iterated more and more until it gets better and better at making these predictions. So here we see more the coding version of the deep learning model. This one is in TensorFlow. The top parts of the graph, it shows you the different layers. So first we have a dense layer, which is basically 512 neurons that take the inputs. And boy, there are a lot of parameters there. 1, 2, 3, that's 12.8 million parameters, basically 12.8 million weight values that can change during the training. Now, I'm not going to bother you with all the other layers, but eventually we'll get to the activation layer. That is the output layer. It has 12 neurons in them, and they represent the 12 output classes, as in finance, economics, marketing, and such. Then we start training this actual model, which you see on the bottom half. Highlighted in yellow is the validation accuracy. Again, that's the validation set I talked about earlier. The training itself is done on the 90% of the data that is the test data. Let's see. Yeah, so you have a loss function, and the aim of the AI in the learning process is to minimize the loss, and that should maximize the accuracy. Finally, we get the validation accuracy. We'll go in this deeper when you do sentences. They have more problems with this. Anyway, the test accuracy end up with 0.889, which is pretty close to 1. And I must say a very good number when it comes to AI. The usual accuracy of AI is between 0.5 and 0.9. So let's make a prediction with our model now that we trained it. So in goes another text. It's vectorized again. Here we see, for example, oh, this is my thesis. So it is material that has not been exposed to the AI in the deep learning training state. That's important because otherwise it knows that one, and there's almost 100%, well, accuracy in predicting it right. It's kind of cheating, but this is my document and this is new for the AI. So it vectorizes it. Again, you see the first number, 1029, that's the amount of the word de I have in there. It goes through the neural network, and out comes a prediction you see in the middle. Well, it has a lot of numbers. The numbers are usually really small, like 1.85 to the power of minus 25. I don't know how to call that. Anyway, one of them is the 1.000. So that's basically with 100% accuracy, it predicts the 1, 2, 3, 4, 5, 6th outputs, or the 5th if you start with 0, which in our labels is finance, and that is correct. Now we get to a more difficult subject, that's sentence classification. Sentences, unlike documents, have not that many words in them, and the words they have can usually be a bit vague, like, do they mean is liquid? Is that a liquid stock market, or is it a liquid company? Very different concepts, could be both. So I started again by counting the keywords, labeling them with my taxonomy and see if that made any sense. Well, here you see, for example, this provides fast, efficient learning updates with immediate feedback and high quality gradients. That sounds like data science. It sounds like AI to me. Yet it came up with business administration. Not sure why. Quality, high, feedback, efficient, well, any of these. So with this technique, I got an accuracy of 47%, which is not that great. So again, let's try to improve that with an AI sentence classifier. For this one, I took let's see, in my knowledge base, I have these 20,000 definitions. So I took the definition of a keyword, which was labeled already. Saves me a whole lot of time by coming up my own sentences and labeling them. Second technique I used, I have abstracts of a lot of research articles that are also labeled on a field. So I took these sentences too. It's not the perfect data set because there will probably be some vague sentences like COVID-19 continues to spread across the world. Well, good luck categorizing that. Or one way of addressing this possible endogeneity problem is through the use of instrumental variables as discussed later in this chapter. Anybody wants to give that a try to classify? But most of the sentences, they are, well, easier for the AI to find patterns in. All in all, I got 52,000 sentences, which is quite a lot, but because it's an automated system, well, it's easier to get a whole lot of sentences in it. Trick I applied to this specific method is word embeddings, or word to vector in this case. What's word to vector? What are word embeddings? It's a computer picks up word associations. I put in my corpus a huge amount of text based on research articles and textbooks of the different fields of business. It takes the words there and associates them with other words. Now, well, I think I'll do a presentation on this on a whole different level because it takes too long to explain here. But the outcome of word to vector is each word is a vector, in this case, a list of 100 different numbers, and they represent an arrow or a pointer, you could say, a pointer in dimensions. And words that are really close to each other in meaning, they get really vectors that are close to each other, as in cash flow and income, or mean and median. This way, the AI, although it might not recognize all numbers or unable to categorize every numbers, it can recognize that cash flow and income are quite similar. It's a technique to squeeze more information out of the few words we have in the sentences to get a successful classifier, at least so I hope. Here we are building this thing again. Now, for this part, I like to concentrate on the bottom half of the training accuracy and the validation accuracy. As you can see, the validation accuracy, it stays kind of stagnant. It's 0.54 at one point and at 0.60. I end up 0.66. You can throw a whole lot more epochs or less in it. It never really gets more than that because it's new data. The old data, on the other hand, you can see in the second column, it says ACC accuracy. It starts as 0.34 and it ends up 0.90. It's way higher than the test validation, the validation accuracy. It's a process called overfitting, as in the computer starts to find patterns in its data set that shouldn't really be there. As you can say, the noise in the signal, it starts to create models based on the noise instead of the signal. These systems work really well on that specific data set, but once you put them out, the generalization aspects out in the real world, they don't make that accurate predictions. So that's why we got the validation data set, the 10% of the documents, to actually test it if it can make these predictions. And this one seems to be stuck on about 0.66, which is already a lot better than the 45% or something I had with my taxonomy. Okay, let's give that a try too. Accounts receivable and payables have their own journal entry in the ledger. That sounds very accounting. I guess it's just the test sentences that can't go wrong. indeed, it comes out with 0.995 in one category, which is accounting and control. Now, I took 100 sentences from different things, different fields that were not exposed to the AI, and it got exactly 66%, which is very close to what the training algorithm came up with it itself. So that is simply what it is. There are too many vague sentences eventually out there, as in the drought in Russia that summer was part of the problem. Is that economy, business administration, something very different? It's very hard to get 0.90% accuracy with sentences. However, a trick I applied, well, a trick or cheating, I don't know, call it what you want. It is the accuracy in the prediction output. Here, the sample sentence, you find 0.995. So it's very certain that this is accounting. And when it's that certain, it's almost always correct with this prediction. If you scrutinize the sentences that were predicted in the wrong field, it's usually a low accuracy, as 0.75 or even 0.50 or even lower than that. It doesn't know. It put it in 5 different categories with 0.2 each, and they are usually wrong. So when ignoring all predictions of sentences with an accuracy less than 0.75, I got to jack up my accuracy to 0.80, which is, well, I would say an acceptable rate. Now, good, I'm glad you made it this far in the presentation, and you may be wondering at this point, like, why is he rambling on about sentences? I get the document classifying, that was explained well at the start about advising keywords, citations, and acronyms, but why the sentences? I can tell you, first of all, I must talk about what does AI do, what doesn't it do? You've seen in the example, there are always a limited amount of output categories. It could be one number, that's a regression. It simply puts out a number for a formula or something. It could be a binary output, as in 1 or 0, yes or no, that is often used. Or you have a limited amount, as in this case, I have 12 fields. You can think maybe 100 of something, but the more you put in output categories, the less accurate it will be. If you, for example, want to extract keywords with an AI and you have 20,000 of them, you're supposed to have 20,000 output categories, and it becomes very muddled. There's never one category that kind of shines and is the one to pick. So for that, I still use my old-fashioned taxonomy. I learned from the great Bill Immen, who invented the data warehouse and is really into taxonomies right now. So we run the taxonomy through the text again, we extract the keywords and we know what fields they are in. So we can do fun things with that. For example, here you see a word cloud that is based on my thesis. Why is the word cloud different? You can see things like value at risk or exchange traded funds, meaning keywords that are supposed to gather n-grams stay together as n-grams, while other things don't know what value at risk is, so they treat value at and risk as different things. But value and at and risk are simply not the same as value at risk. Another thing is that you only see keywords, the business terms. It doesn't use the term red or 12 or simply or something. Only keywords. So in one glance, business-wise, you see what it's about. Portfolio, value at risk, exchange traded funds, commodities, futures. It's about commodity investments and how pension funds can diversify their risk. Anyway, a bit of subject here. So let's go on. Now we know all the keywords and we know what category they are in. We can do text analytics. Here's a representation of a tree graph of my thesis. And again, it's finance and investments. That's the biggest category. But as you saw in the taxonomy, it has finer details about subfields and subjects. So within finance and investments, you have financial derivatives, which are options, futures, all kind of, well, financial magic. And of these, you can see, oh, he read about future derivatives. He wrote about commodity derivatives. And this way, you kind of categorize in a very detailed way. I'm still working on this tree graph. You're supposed to click on it till it goes to the finest details of, for example, deep learning within data science, artificial intelligence, and then it should give you your little vocabulary. You use the word CNN 12 times and RNN 20 times. But you still get a great idea of what your thesis is about. You might be worried if you're writing about finance and accounting and control is your major thing. And this happens to students a lot. So the student then will be wondering, okay, I get it. I should write more about finance and less about accounting, but I don't know where I went wrong. Tell me where I'm writing about accounting. That's, of course, where the sentence classifier comes in place. It tokenizes sentences in your document, and it simply runs them through the classifier model, and out comes the prediction. In this case, anything in blue is finance, anything in red is a different field. So you're notified of where you wrote about different fields. Gray is the unknown one, as in the accuracy was too low to test it. Another thing we're working about at GILO is transactions. As in, you wrote a paragraph or two about a certain subject. We can tell this about the categorization. Then you're writing about a different subject. So it needs a transition. It needs a bridge to put the reader there. Otherwise, it's just poor writing from one thing to the other. Okay, well, we're getting to the end of it. Conclusions. What have we learned from this presentation? Well, first of all, NLP models, they don't speak English. You must convert text to data. And this is simply true for about any NLP application, AI or not. The second thing is that artificial intelligence, well, it's not intelligence, it does pattern recognition. And to really get something useful for humans to put in an app to say this is a great function, you usually have to combine the two. You use AI to understand patterns that it does really well and really fast, but then you still need some human knowledge in case in our taxonomy to make sense of it or to put the dots on the I. Third conclusion is it's much more challenging to classify sentences than words. Basically, the more text you have in whatever you're classifying, the easier it becomes. Yes, it's quite obvious. One thing I haven't talked about is lopsidedness, especially in the sentences. My data set was quite lopsided. Some subjects, especially marketing, had the most sentences, I believe 12,000 out of 50,000. Because it had the most definitions and abstracts in the system I used to extract the sentences. Other fields like real estate, they were pretty small. They had maybe 1,000 or 2,000 sentences. So with the lopsidedness, it still makes predictions where sort of predictions go well. But when you look at the predictions that are wrong, it's often that it predicts marketing because it's exposed to so much more marketing instead of other things. It simply says marketing too often because, well, it seems to know a lot more about it. So we need to fix that, and I don't want to omit a lot of data. So I'm working on getting more data on the other fields. Let's see, what else did we learn? Yes, data sets. They are a lot of work to put together often. So once you have a data set, you want to use it for different things. And with handy scripts in Python, you can often extract, transform a sort of ETL model, exchange, transact, transform and load. So you can easily use them in the second or third categorization or any model. As in, I took the documents, I classified, and somehow I was able to extract sentences and use that in the next data set without doing the effort of creating one. Okay, and maybe the final conclusion, and this is the most important one for you viewers at home, that deep learning models can be complex, but they're not that complex. You can learn them too. If you have a technical background, if you have experience with a bit of coding, maybe you have an experience with math and statistics that also help, you can learn this material. And by now, the technology behind it, for example, TensorFlow and PyTorch, they're not easy to understand, but you don't need a PhD in physics either. So I'm going to do more presentations and we're going to guide you through this, and then it becomes a lot of practicing at home. Very well. Questions are a bit hard for the presentation, so we're going to leave it at it. I hope you enjoyed my presentation. I hope all became clear, and I'll see you again in the next one.